Good evening,
Now, sir.
everyone, and welcome to a new webinar of the Iraqi Medical Physics Society, the IMPS. Today, our guest is Professor Carlos Almeida. Professor Carlos Almeida is an emeritus professor in medical physics in the Department of Radiology Science, University of Rio de Janeiro in Brazil. He graduated with a physics degree from the Federal University of Bahia in Brasilia. And he also has an MSc in medical physics and PhD in radiation biophysics from the MD Anderson Hospital, University of Texas. He got a postdoc degree, and he has worked as a visiting scientist in famous fields. So he worked in Roswell Hospital in Buffalo, New York. He worked in Gustave Roussy in Paris, and he worked also in Marie Curie Institute in Paris. He get a board certified from the American Board of Medical Physics, the APMP, and he board certified from the Brazilian Nuclear Commission, and also he's board certified by the Brazilian Association of Medical Physics. He has a lot of professional activities. He worked as a full professor in medical physics in the Department of Radiology, University of Rio de Janeiro. And he's a founder and the chairman of the Department of Radiological Science in the University of Rio de Janeiro. He's a member of the IAE Secondary Standard Dosimetry Laboratory, and he is expert of the IAEA and several scientific and educational projects. Dr. Almeida, he has awarded the title of a fellow from the MD Anderson Hospital in Houston, and he also titled as a fellow in the American Association of Physics in Medicine, the AAPM, sorry. And he also awarded a medal from the Brazilian Navy and awarded a golden medal from the Brazilian Society of Radiation Oncology. And also, he is awarded bricks from the Becquerel Academy of Science, and he is awarded a fellow degree from the International Organization of Medical Physics. He has a lot of publications. He published around of 200 papers, many of them in medical physics and biophysics and radiology, and several books chapters, including the technical report of the International Atomic Energy Agency. Now he's finishing a book on special topics in medical physics and radiation protection. Dr. Carlos also is a member of examining committee of several MSc and PhD students in Brazil, France, and Argentina. He's supervised around 68 MSc students and around 28 PhD students. And he's a chairman of 2 research projects in International Atomic Energy Agency and chairman of 2 research projects in the National Research Council. And also he's a coordinator for research project in Rio de Janeiro state. It's a very, very interesting CV, Dr. Carlos.
Thank you very much.
Dr. Carlos also, he's mastering 4 languages, the Portuguese, which is his mother language, English language, and French and Spanish, which is wonderful. Thank you very much for being with us today, Dr. Carlos.
Well, it's indeed a great pleasure to be with all of you. You know, as I mentioned, we are 11,000 kilometers away, and somehow internet today put us together, you know. And I'm sure that the Medical Physics Society in Iraq is very active, and I'm very, very pleased to be, you know, even by online with all of you. And I hope that this discussion will enlighten your view of the basic concepts involved in dosimetry. Thank you very much. Next slide. I'd like to say Massa Alcahai, which is good morning in Portuguese, or bom dia in Portuguese. And next slide. Just to organize a little bit the thoughts here, the lecture contents will be divided in about 11 topics. The first one is the main objectives. Then I'll talk a little bit about the conceptual confusion of some of us and also some of the manufacturers about the basic understanding about the quantities, how to achieve our objective as a medical physicist, what is the metrological network and the BIPM role, what is a primary lab, what is a secondary lab, and the use institution, which you mean your institution, probably my institution as well. And what we do there, normally what we do is a reference dosimetry, beam calibration, relative dosimetry, and relative measurements that are very much related to the treatment planning system and to the patient treatment, the cancer patient treatment. At the end, we just say a few words, and I'll leave some reference, not very many, but the ones that I believe there should be complement what we're discussing here. Next slide. What is the main objective of our procedure? Well, to measure one of the quantities that are very much related to our fields. The quantities of air camera today is more related to low energy X-rays and also to radiation protection, and absorb those that we need to fulfill a specific application. For instance, on the right side, you can see a 3D dose distribution of iodine 125 seeds that were inserted into a prostate cancer being treated in a very conformal way, because in fact, all the implants, all the source implants generates a very conformal dose distribution. Next slide. The point that I want to make here is that sometimes we make confusion also, we are added by the manufacturers about what is an absolute dosimetry, what's a reference dosimetry, what's relative dosimetry, and what instrument should we use to perform those measurements. Next slide. For instance, if you go to the one of the big companies, American companies called Standard Imaging, you see there on the pamphlet a lot of confusion what they describe. They say it's a precise setup. They call it absolute dose measurements. And they say, again, absolute dosimetry, and they say that supports the WAPM TG51, also the IAA TRF 398, but probably you're using that in Iraq. But in fact, the TRF 398 does not mention absolute dosimetry, because this is not to us to do that, as I've showed to you. We talk about reference dosimetry, we talk about relative measurements. Next slide. IBA, which is a big company also, they say precise QA solutions offers a complete range of solutions for absolute dosimetry. This is not quite true. What they are selling are instruments they're using for relative dosimetry and also for reference dosimeters. They do not sell primary standards. Next one. PTW, it's a German company that you also probably know. They used to use the word absolute dosimetry, but I once talked to Mr. Pitchlau about this, and somehow he was convinced that he should not use absolute dosimetry. Now he's using reference dosimetry. In just one case, is that they are now selling a primary standard for air camera for radiation protection. So for that particular instrument, they can call it a primary standard. Next slide. What is important? Important is that what we measured, must be the best value possible, most carefully done, and we should use calibration coefficients and correction factors to adjust the measured value to the true value. So this is several steps involved only when you are just measuring in a particular situation, either in air or in water phantom. Next one. Second, the measurement results made by different institutions must be comparable. In other words, you in Iraq should measure the gray the same way that I measured in Brazil. So why is that important? Because the next slide, it's important because because the clinical results, only can be compared if at least one of the parameters which absorb those is measured the same way by everybody. And besides that, we have to remember that besides the dose value, you have the biological and clinical parameters that should be well known and fully described. So if we do our job, which is measure the quantity absorbed dose well, and everybody's measuring the same way, following a protocol that I mentioned a little bit later. So at least our part of the job is well done, okay? But when you look at a cell survival curve, you know, in this case, for instance, for prostate, everybody could somehow compare the same results, okay? Next slide. The next one. In order to do that, you know, what we should do is to use a protocol or use some code of practice like the one that the IAEA has proposed in 2010 and is also being upgraded recently. When we say using a universal protocol, it means that we must use the same reference conditions, you know, the word they will see later, the distance source to the surface of the phantom, the field size, and the depth where we place ion chambers. So this is called the reference condition. So this is the condition where you see a calibration lab would provide you a calibration coefficient, and that's the reference condition that you should use in your institution. And the quantity that you are measuring, you know, this quantity, in this particular case, absorbed dose, must be referenced to the standard of the BIPM as it was decided by the Metro Convention. The next one. It's also important for us that we are radiation workers, that we also are able to measure the radiation quantity very accurately to protect ourselves as radiation workers. So we should know what is the intensity of the radiation field. We should know how long are we able to work in that particular field. And to do that, somehow we must measure it the best way possible to protect ourselves and to protect our colleagues. Next slide. Why is it important when we talk about the International Meteorological Network? It's very simple. When I said you measure in Iraq or you measure in Brazil, somebody measure in France, you know, this means that we have a network of laboratories that are involved in these procedures, you know, and those laboratories, you know, they are located in different countries, and they provide the standards, the primary standards for air chem and absorbed dose to water. Next slide. And when we talk again about the International Network of Ionizing Radiation Metrology, we can see this slide here, which shows the LP, which is the primary standard. The second level is the secondary standard dosimetry lab, which also the IAEA has a lab to provide calibration to the SSDL. And then the users, which are us at the labs. But here in the center, you can see BIPM. The BIPM is, as I mentioned before, is the organ has been decided by the Metro Convention to coordinate the comparisons among the primary standards to make sure that everybody is measured the same way. In the next slide, show you an example. Next one. For instance, we have primary standards in Canada, Germany, US, France, England, and several others, but not all the countries have primary standards. And we don't need that because it's very complex, very sophisticated. You need equipment, computer control systems, experimental arrangements, very skilled staff, and the constraints involved in measuring those quantities are very, very tough. So this procedure, I can say that it's almost impossible to be reproduced at the hospital level. Next slide. And here's an example of what does the BIPM do, you know. And we talk here about 3 different systems that measure the absorbed dose to water: the water calorimeter I'll mention later, the graphite calorimeter, and the freak dosimetry. Look at all those labs, you know, here you can see in the back of the different labs that I mentioned to you, some of them. And the variation among them compared to the BIPM is less than 0.5%. You see the squares are graphite calorimeter, the black dots are the water calorimeter, and this one little one here is the freak dosimetry that I'll talk a little bit about in a moment. So that was as important for you to realize that when you measure at the hospital a particular quantity, this quantity is related to the calibration lab that has provided you with the calibration coefficient. And that lab, if it's not a primary standard, if it's a secondary standard, this lab is connected to the primary standard. And the primary standards are all connected to the BIPM. Next slide. Now, the two ways of measuring, a radiation beam, either if you're looking at air camera, that you received NK, which is the calibration coefficient for air camera, or DW in water with the calibration coefficient for water. Either one, you can come down to what is really interest to us, which is the dose to water, because this is what is we refer to the dose to the patient, as you well know, this is the similarity between the tissue and the water. So very little correction is done to adjust for that. Next one. Now, the primary standard dosimetry lab, what do they use? They use free air chambers for air camera standards for low and medium energy X-ray beams up to 400 kV, from 30 kV to 400 kV. They use different chambers depending on the range that you have to measure. The size of the chamber is different. They use water calorimeter or graphite calorimeter for absorb those standards to water or to graphite, and then you have to convert from the graphite to water. They use the freak dosimeter as the standard for absorbed dose to water, which is a chemical dosimeter. Ionization chambers that requires a well-known volume as a standard, for instance, for air camera, when you use for gamma rays emitted for cobalt-60, or even for absorbed dose to graphite that you can use for a large variety of photons and electron beams. Next slide. So the absolute dosimetry means that you must measure the particular quantity according with this definition. For instance, exposure is charge per unit of mass. Dose is energy deposit per unit of mass. So to be consistent with that, your instrumentation must have this quality to measure the quantity the way it's defined. Next one. Now, free air chambers, you can use it from 5400 kV. The wide angle free air chamber, which is a new one, it's the standard for seeds of iodine 125 and also palladium 103. And also the cavity chamber for gamma rays from cobalt-60. Right, next one. What is a free air chamber? Free air chamber is a big box it's a metal box with a collector here and two guard rings, and then the high voltage is equally applied to all three. You have the radiation field comes into a diaphragm that collimates the beam. It passes through air layer with this dimension, which is the layer required to provide the electronic equilibrium. And this volume here, L, is the volume where you collect the ions produced by this amount of air. So you don't have a wall in the chamber. That's why it's called free air chamber. The chamber that we use in the clinic is a chamber that has wall. This one does not have wall. It has only air with sufficient thickness to provide electronic equilibrium. Next one. This is a picture of the free air chamber inside. You see how how high voltage plates to maintain the electrical field between the collectors and then the guard rings in a way that the volume is well defined by those lines. Next one. You see here, this is electrical lines between the two guard volume. Next one. It's not that simple, For instance, now this one, thank you. not that thing, for instance, the air camera, it requires a number of factors and also parameters in order to typically transform what you measured in the real quantity that you want. And in this situation here, you have this equation here. What's important? The most important ones are the attenuation of the primary beam in the column between the diaphragm and the collective volume. We have some attenuation here. Also, they have the ionization loss by the electrons in the electrodes, here. Also, you have the air density, which depends on the temperature, pressure, also the humidity. In this case here, you add a little bit more correction, considering that the air does not follow exactly the perfect gas law, so you have a small air compressibility factor. And then the sensitive volume of the chamber, which changes where charges are produced and collected. This has to be well done, because this is the area where you're going to rely upon this point here, the volume, and to define the air camera for the X-rays. Next one. When you talk about iodine 125 and palladium 103, what you use the wide angle free air chamber means it's a chamber that it's very wide, and you can see here, this is the source. Then we have a distance to the center of the sensitive volume. Here's the two guard rings, and this is the electrodes. This is connected to the electrometer. Then you get the walls close together, but you keep the distance from the source to the center of the collecting volume the same. This is a very, very sophisticated system, even more sophisticated than the free air chamber, which exists for more than 50 years. The wide angle free air chamber is something recently. The next slide shows you a very sophisticated wide angle free air chamber in the French lab. You can see here the source. This little black dot here is the source, which is this one here amplified. It's placed inside of this big ring of several plates, and the signal is collected by the whole ring that has collectors and also guard ring. This is a very sophisticated system that's now being used in France. The next one. The major corrections that you have to take into account is the attenuation of a filter that's placed to absorb some of the low energy that you're not interested to the clinical side, which is in the order of 2%, and the source aperture attenuation also in the order of 1.25%. The rest of the corrections are quite small, almost close to 1. But to handle this particular chamber, it requires a lot of time, a lot of effort, and a very skilled staff to do that. Next one. Next. Now, when we talk about the air camera for gamma rays for cobalt-60, since we use that for many, many years. Next slide. It shows the graphite chamber that we know the volume. But this is the wall of the chamber. This is the electrode, which is the same material as the wall. This is graphite. And then you measure the volume without the electrode. You insert the electrode into the chamber, and you add this little portion of air, and then you have measured very accurately the volume of the chamber. Now you remember that what we aim is to measure the dose in a particular point in air in the absence of the detector. But it's not possible to do that for cobalt. For instance, to use a free air chamber in cobalt, we would need a very big instrument, because we need a very large thickness of air to provide the electronic equilibrium. So we use a solid material like graphite, or we use a PMMA also with that. As we do that, we're introducing some material is different than air, or graphite or PMMA. So we have to make corrections for that, okay? The next slide, it gives you some idea of the size of the chamber, you know, now in position being irradiated by a cobalt. Next slide. You can see that the equation to do that, this one is not very simple, you know, because you have to take into account the ratio of the stopping power between graphite and air, because as you create a wall which is different than air, you have a mass absorption coefficient that, so for the electron, complicated in terms of measuring this quantity, you know. Next slide also shows that several of the parameters have to be taken care of. And the most ones are the correction for the scattering in the chamber stem, you know, in this area of the chamber. Then the correction due to the attenuation of the wall, because as you introduce the wall, you know, generate, and you remember that the wall has several functions. One is to generate electrons that will provide and create ionization in the chamber. So in this process, you have some attenuation. You have also the where in this wall, you know, is the point that should consider to be the point of production, where the electrons originates, that's going to produce the ionization side of the chamber. That has to be calculated by Monte Carlo, or you can do experimentally, but the best way to do is Monte Carlo, okay? Mass, temperature and pressure, this is very simple to do it, you know. Vapor pressure also is not a problem. And leakage, normally for this type of chamber, and when you're considering that you're using a very high quality electrometer, it should not be a point of concern. But those 3 points is yes. Next one. Now, when we talk about absorbed dose to water, that's a completely different ball game, let's say. That the next slide shows that we have the first option is to use a graphite chamber, a pure graphite chamber with 99.99 graphite inside of a graphite phantom. You know, this chamber should have these dimensions very well measured, so you know accurately the volume. And then you're exposed to a field size of 10 by 10, you know, like we said, under the reference conditions. And in the next slide will give us some idea of the corrections they have to do for that, you know. And the main corrections are the sensitive volume, the ratio between the mass energy absorption coefficient for water and graphite, because you're measuring this in a graphite phantom, you know. And then you have the ratio of the stopping power between graphite and air, calculated based on the Spencer-Atke theory. And then you have several correction factors like humidity, loss of ionic recombination, radial non-uniformity. And then the most important one is that now you have to convert the dose from graphite to water, because that's what you want. And so you use this F factor here as a factor that makes the conversion between the dose measured in graphite. And as I said, the chamber is pure graphite, but is in a water in a graphite phantom. And what we need is the water equivalent in the dose equivalent in water. The next one. The second possibility, in fact, can divide in two, is the water calorimetry and also the graphite calorimetry. The next one show us the water calorimeter was devised by Steve Doman when he was working at the primary standard lab in the States. And what you see here is a water tank. Inside of the water tank, we have these two temperature sensors. You have a sheet of brass on the top, and you have a styrofoam here to isolate this water from the room. And then you have a steering magnet to make this water revolve, you know. And also you have the glass vial sensors, which is, this is where you place the thermistors. And those thermistors are calibrated, the national physical labs in each one of these countries, you know. So this is an enormous amount of work. To set up this calorimeter takes a few hours. To make measurements, you have to be extremely patient because you have effects due to the heat effect of water and the effect of those vials and so on. You know, it's very, very, very complex system. And the next slide would give us some idea of, for instance, just for you to have an idea, that 2 grays used to expose this calorimeter provides only 1 millikelvin of increase in temperature. And normally, when you are working with that, you have 3 different regions. One is the pre-drift, which is, I mean, you have no beam. This beam, which you have a linear increase, and then when the beam stops, you have a post-drift. And normally, you take this region here as a reference region for your quantity that you're evaluating. The next one. See here you have just to have an idea of the complexity, you know. This you have the specific heat of the water factor. You have the transit effect of the thermistor response due to the dose deposition, conductive transfer heat due to the excess of heat from the glass components where you have the sensors. And then most important one is the heated effect. That is the difference between the absorbed dose, the absorbed energy, and the energy that appears to be as a heat due to chemical reactions induced by radiation. This is, you have the heated effect for all the materials, not only for graphite, but also have for water. So this is not a very simple instrument, but it's let's say it's the most conceptually is the most applicable type of instruments to measure, truly measured, absolute measured, absorbed dose to water. The next slide. Then the other system that we have is the Frick solution, which is a chemical solution. It's a ferrosulfate solution that when you irradiate this solution, the absorbance of the solution changes. And this difference in absorbs, which is measured by for this method, you have to know in a very, very accurate way what is called the G value, which is which measures the transformation of the ions ferrous in ferric, and this depends on the quality of the beam. Other than that, everything else is very simple because you have the delta OG is the difference in absorbance. The DF is the dose to the Frick solution. L is the thickness of the cell. The density was very close to water. This is one of the advantages of this method. And this is the extinction coefficient, which is a chemical parameter, must be well known. Next one. The absorbance is measured using a spectrophotometer. This is a dual light spectrophotometer. And this is the cell where you place the solution after you irradiate it. You have this dimension here, which is L. Then you calculate the dose to the Frick solution this way, you know, by dividing the absorbance by the G value and the L, and then the density and extinction coefficient. But then the next step is to transform, you know, by using the appropriate G value. As you can see here that from few kV to 10 MeV, it's a very, very interesting curve that so you must know what is the mean equivalent energy of the beam that you are considering, so you can use the proper value for the G. Next one. Now what you have to do, once you know the dose to the frequency, now what you have is dose to the water, and this one corrects for the inhomogeneity of the dose deposit the fixed solution. This is the fact. This is because you require a certain volume of solution to irradiate it. So when you, let's say, 2 to 5 cc of solution. So when you perform the irradiation, in fact, you're not measuring one particular point, but you're measuring the volume. So you must know this distribution and make some correction factors in order to get the dose to the minimum volume possible, which is the volume that you're interested to measure and later correlate with an ion chamber. The next one. And if we go back now to the graph, it shows that all three methods, now this green one with those here are the water calorimetry. Those are the graphite calorimeters, and this particular one is the ferrosulfate. All of them are compared with the BIPM as reference. And you see that fixed solution, but in general, it's less than 0.5%. We in our lab in Rio, we are one of the few labs in the country at this moment that works very heavily with ferrosulfate, and we can say that we can dominate this process. And the comparisons that we have with the NRC from Canada, it's within 0.5 to 0.6%. Next one. What is the secondary standard lab? This is probably very important to you because the connection between you and the first lab in the metrological network is a secondary standards. Secondary standard lab is the lab in each country, and I think you have one in Iraq, at least is listed. It not be operational or it's in operation. I don't know exactly, but it is the link between you and the international community, as I mentioned before. It's a link between you and the international metrological network. It's a link between you and all your colleagues everywhere in the world. So it's a lab which uses the best possible metrological instruments, and normally they are recognized by the national lab as responsible for disseminating the quantity to the user, and also somehow as the IAEA advises the network. And this, I might say, the IAEA has done a tremendous work, because in the last 25 years, they have installed almost 100 labs around the world, and the deviations from measurements the first slides that I mentioned is your connection to the different hospitals that you have here, is a connection to the clinical results that you have in your city, in your country, and everybody. Next one. So this SSDL is recognized and accredited by the country's meteorological authority, and I'm sure in Iraq you have one. And it's not only responsible to disseminate the quantity, but also to follow the users. When we provide as our lab, we do that for instance, for high dose rate region 192, and we provide a calibration coefficient for well-type chamber. We also try to use auditing systems to make sure that the user are using the calibration coefficient the way it should use. So this is also one of the rules of the SSDLs. Next one. The location of the SSDL, it varies in each country, but that's where you should have all the standards for diagnostic and treatment machines, and also for the nuclear medicine reference to calibrate the well chambers used in nuclear medicine. And what they do is to use the formalism of the TRS 398 or TG 251, like the Americans do, you know, and in a very standardized way, in a reference condition, so or everybody will be measuring the same way. Next one. In this situation, you know, now at the user's level, which is our level, if you have just one instrument, you have to use it very carefully, because if something goes wrong, you don't have any instrument to measure. But if you have two instruments, which is advisable to be, we select one as a reference instrument, the one that one of the two that has the best stability. And then the second one they use as a field instrument. They use the routine basis. From time to time, you do a cross calibration between the field instrument and the reference instrument. And then when you have to send one of the two to calibration to the secondary standard lab or to a primary standard lab, you can use your reference instrument and keep the field instrument in the institution. And when the instrument comes back, then you could perform a cross calibration to make sure that the field instrument is working with the same qualities as before. Next one. Now, the basic instruments that we need on the hospital, you know, is a water phantom. You need a good barometer, you know, and this is probably one of the most common mistakes that the medical physicists do when they use make measurements in high altitudes. And one mistake is to call the airport and ask the airport what's the pressure in there. And if the airport is the same altitude as you, it's probably okay. But if it's not, you know, you may be making mistakes. The thermometer, you know, this particular one here is mercury thermometer, but it's becoming more and more out of use because of the mercury is a very contaminant element. So we're mostly using digital thermometers. A thimble chamber, then a pinpoint chamber, and this is for diagnostic, and this particular one is for electrons. This is the whole armamentario that we did. I just want to draw your attention here. You see this one has, this cable has a cap, you know, this one doesn't have a cap. And let me tell you something, all those connectors must be, you must use a cap to avoid humidity problems. If you don't have a metallic cap, you just put an aluminum foil and make a rubber around it and keep it safe, okay? This is the most likely the highest point of problem in our ionization chambers, not only in the cables, but also in the electrometers if they're not keeping in a place where humidity is controlled, humidity, dust, and so on. Next one. Now, what we do a beam calibration in our level with a water phantom with here with a linear accelerator, you know. The next one, next slide. Here, what we should normally do is to use the same beam quality as the one used in the SSDL, okay? And use the same reference conditions like the SSD 100, field size 10 by 10, and depth of 5 centimeters. But it's true that very few institutions nowadays still have cobalt 60, and the calibrations are done in a cobalt 60. If you use a cobalt 60, it's very simple too, because you have the the readings of the instrument corrected for the influence quantities. And when you use the calibration coefficient, and you have straight the dose to the water. But the next slide, if you are using a different quality, like if you use a 6 MeV beam or 10 MeV photon, 15 or 25, whatever, you know, and your calibration coefficient for cobalt, not for that particular energy, then you must use what we call a KQ factor. You know, they should take into account the difference response of the chamber. And so in this case, you know, to define the dose to water for this quality, which is not the Q0 for cobalt, you have to apply the calibration coefficient. The calibration coefficient was provided to you for cobalt 60, and use the KQ factor that is required to correct the chamber response. The next slide, I'll show you what is that. You know, you should be careful because the KQ value, it depends not only on the beam quality, and here, for instance, this blue line here is somewhere the beam quality of a 6 MeV photon beam, but it depends on the chamber that you're using. You see, it could be a 2-3% difference from a PTW chamber to a X-radium, for instance. Why is that? Because every chamber has a different constitution, different materials on the wall, different materials on the electrode. And by having that, and going back to that equation, you have this, the mass energy absorption coefficient differ for each one of this. So the interactions are different, the absorption are different, the scattering is different. So you must know exactly what is the KQ value for your chamber, for the quality of your beam. This is you can find in several publications like the TRS 398, and also for some chambers that were generated after the 398, you can find in the literature. And what is important is to define this beam quality, like you see. This is for, as I said, is about here the 6 MeV, then is 10 MeV and 25 MeV and so on. In the next slide, as you know, the beam quality is defined by the tissue phantom ratio, which is measured, which is a ratio between two readings, between 10 by 10 field size at 20 centimeters of water for the same SAD. Then you measure a 10 by 10 at a depth of 10 centimeters, and the ratio of the 20/10 is what we call the TPR, and also what we're going to relate as the quality of the beam. Okay, so this measure must be done very, very careful, because as you remember on the previous slide, can we go back to the previous slide, please? Because you remember that this could be responsible for a very large variation if you don't have the beam quality well defined, well measured, okay? And if you don't have also defined for the type of chamber that you're using. Next slide, please. Next one. Then you must remember, it's very simple, but I think I should mention that when the chambers are sent to the calibration lab, if they are non-waterproof chambers, they put the chambers in the water at the reference depths, and they perform the measurements. But if the chamber is not waterproof, they have a PMMA cap that is also used in the SSGL, and you have to use that, okay? So remember that. Don't mess up, because if it's non-water and you put it in the water, you will just destroy the chamber, okay? And just remember that you have to reproduce what the calibration lab provides to you. Next one. For Iridium 192 sources, we can ask how I can calibrate those sources, you know? Normally, we use a well-type chamber, and this, for this energy, you know, which is has a very broad spectrum, and the average energy is about 400 kV. What we have, our lab has proposed and has been accepted for the IAEA, that we measure the air camera for cobalt 60, and then we measure the air camera for 250 kV with 3 millimeters of copper for HVL. And then we made a weighted energy, because if you look at the spectrum, 80% of the contribution of the iridium source is around 250 keV, and 20% is in the region of cobalt. So we measured a weight of those two numbers, and then we get the air camera for iridium. That's the way we do. That's the way the Americans, the IAEA has recommended. But what the Americans do is the only country, they use a cesium source, cesium and 250 keV. And the problem is that very, very, very few labs have cesium teletherapy old sources. So in order to be independent of the American philosophy of not having to send the chambers to the United States, you can use the NK cobalt at 250 keV, and you are doing very well with that. Okay, a comparison has been done. It's published in Medical Physics, and the results are very much comparable. Next slide. Now, what are these uncertainties that we have to remember? That we have to face. And remember, the uncertainty is not a variable. Uncertainty is the probability that you can find that particular, the best value of the quantity within a certain interval. So what you have here is the NDW calibration of the PSDL is 0.5%. Long-term stability of the secondary standard is 0.1. Then the NDW calibration is 0.4. And in this step of the standard lab, you have a 0.6%. When it comes to our level, then you have the several additional factors that changes this 0.6 value to 1.4, like the reading, your correction for influence quantities, beam correction factor, which you use the calculated values. And then when you combine those two, you have 1.5% with K equal to, or 95% interval confidence. So this is what the 398 suggests. That's what we should do. You can ask the question, well, can we do better than that? I'd say, yes, we could, but look at here, the KQ value is most responsible for the increase that it's have a high uncertainty because of the stopping power values, which are still not as well known as we would like to have. And second, we don't have yet several labs that could provide you with the calibration coefficient for directly for a 6 MeV or for 10 MeV or 25 MeV. Some they are doing now, like the British, the Germans and the Canadians now. But they also perform the calibration for the beam quality that they are using the LINAC. So they specify the beam quality, then you have to measure the beam quality so you can apply the calibration coefficient specifically for that point. So the gain in using a calibration coefficient directly for the 6 MeV or 10 MeV is not very high, maybe reducing here 0.5% in this overall uncertainty. Okay, next slide. Now, at the user institution, then when you talk about the relative dosimetry, you can use several types of detectors because none of them requires calibration, and all the measurements are relative to the point of maximus. So you can use diodes, TLDs, OSLs, diamond films, and more chambers. Okay, next one. And those detectors, they can be used to measure percent depth dose, and you can see here a very specific region, which is a build-up region to the point of maximum, and then you have a decay here with the linear fall off for the curve for this particular beam. And this point of maximum, as you see in the next slide, and also the maximum dose at the surface changes with energy. Next slide. You can see, for instance, this is the 4 kVp photons. This one here, you see the maximum dose at the surface. But as you go from cobalt, is point of maximum is about 5 millimeters. Then you go to 6 MeV, which is about 1.2, and 18 MeV, which is about 3-4 centimeters. And the shape of the curve is about the same, but this region here is very important to know because of the clinical application. And why do we use a 5 centimeters? Because we are just about here, away from these large gradients that surround the point of Gmax. The next slide. Now, also the measurement of the beam flatness, you must have a detector which says a resolution good enough to see what is happening here at the penumbra area, and also in this midpoint. This is even more important now that we have a flattening free filters where the distribution is done in a little bit different way. Next one. For electrons, the same, you must have a detector that could see small differences, on this graded region, which is very, very steep, but you must know that. Next slide. In the depth dose curves is even more critical because this is the data that you enter into the treatment planning system to do the dose calculation for the patients. And you must have a detector to be able to see the difference here, on this physical penumbra area. What normally do you measure the flatness in different depths with the detector. So you enter this data in the treatment planning because it's very difficult to identify just looking at this number and this dimension. Next one. Also, when you measure the output factors, this is interesting because you see here, this is, that it's a very typical one. But this is good to see because, for instance, this blue one here is for the 6 MeV, but this one here is for the flattened free filter of photons, which coincides with the 10 MeV beam. And this one here is for the 10 MeV flattened filter free beam. And also on the lower end, on the smaller field size, the shape, it changes a little bit, So you must be careful when you measure those output factors, when you are normalized to the 10 by 10 field size, which this is the way it's done. If you're measuring with a flattened filter, a physical flattened filter, or if you're measuring with a flattened filter free, okay? You have to be careful with that. Next one. Now, the key points to be considered before you make relative measurements, if your detector has an energy dependence with the depth of water, because as you see, as you know, as you move inside of the water, the energy fluence changes. So if you have a detector that's very sensitive to energy, they be providing the wrong signal. The dose rate dependence, especially for the flattened filter-free beams. The directional dependence of the detector, depending on the geometry, also the volume and the size. The signal-to-noise ratio is a function of the field size, detector shape, and size, and the signal itself. The sensitivity, and the defect is caused by dose storage that may result in the loss of spatial resolution. Like, for instance, the TLDs, after a certain amount of dose that you cannot use them anymore, or some diodes also they after certain dose, higher dose, they lose the spatial resolution. Even though some of the diodes have been now or compensated for this damage, But for instance, when you're using a panel with for electronic portal image device, you must remember that those detectors somehow will eventually lose some response. And that's why you also have to make some quality assurance to make sure that all detectors on the panel are provided the same information. Next one. So the final, let's say that the primary standards that we mentioned, like the ferrosulfate, the water calorimeter, graphite calorimetry, and also the chambers, the free air chambers, they should only be done in standard labs or in some very comprehensive research labs. The next one. Next, Reference dosimetry is what we do in our institution. That's what you do in your institution, using the calibration coefficients. But you have to remember that KQ factor may be needed if you're not using the same beam as the beam that the chamber was calibrated. Next one. The relative dosimeter, the user institution, there's no need to use the NDW. So as we mentioned, you can use several detectors as long as you keep track of the response of those detectors, keep track of the stability of the systems, and also keep track of the damage that may occur to those instruments. Okay, so now I think you are, it's very clear to you what is a primary standard, what does the primary standard do to the calibration lab, to the secondary standard lab, what the secondary standard lab does to us, and what is our role, which is directly connected to the patient, what's our role directly connected to everybody else in the country, in the world, to make sure that we are measuring the quantity the same way. Next. I give some reference that you are easy to find, if some of you wants to know a little bit more deep into that. And there's hundreds of references, but I picked this one because I'm sure that's going to be easy for you. Next one. I thank you very much. I would like to say, I'm not sure if I can pronounce correctly, but Shukran Laka. This is a picture of Rio de Janeiro, where I live. This is the sugar loaf you must have heard about. Has a little system that brings you from this point to the ground level, and then up here. It's a beautiful view. Next one. I thank you very much, and in Portuguese we say muito obrigado. Okay. And last but not least, the next slide, I'd like to say that I'd like to see you in Rio one day, if you come. This is very much close to where I live, somewhere in here. So if you ever come to Rio, please make sure that you contact me so I can help you to get around. Next slide. And now I'd like to just say something that I keep saying to my students, that ignorance is a transitory state. So don't be afraid to ask if you don't know, but be careful to say that you know something that you don't know, because more we know that how much we don't know. But ignorance is transitory, but the stupidity is for good. So remember that, okay? Don't be afraid. Don't be shy, but be professional. Thank you very much, Shankar. If you have any questions, I'll be very glad to answer them. Aladdin?
Thank
No.
you, Professor Almeida. Thank you very much for the important information you provide us in this presentation, and thank you very much for the kind invitation to Rio de Janeiro to visit. Now we open the door for the questions from the audience. So please, if you have any questions, you can ask Dr. Carlos Almeida about the dosimetry on the primary and the secondary labs and the importance of getting the quantification of the dose in very high precision. Please, if there's any question.
I can see that we have 45 participants. So I'm very pleased that everybody has kept awake during the whole conference. Thank you very much for that. I also can see
any questions?
Somebody writing in Arabic.
So yes, he's Alaikum salam. You can
Yes, I can talk.
Yeah,
My
you
name
can
is
speak in English,
Afnan.
please.
Yes, I can speak English. My name is Afnan. I'm from Karbala Hospital, Al Hassan Mushtaba. I already work in radiotherapy center. I want to ask doctor about the WD and the permissibility number. I already calibrate my ion chamber from ABA. Last week, there's a different in WD, 1.5. It's how many permissibility, the different
Well,
between the previous one and the second one. I sent it to Turkish SSDL, and they resend it again to me in 1 week. And the difference, it's like one.
yeah, that first of all, that you had a reading equal before you sent and after the chamber came back, just to make sure there was not a change in the NDW, but also change in the chamber response. Did you do that?
Yes, yes, we do that.
Okay. How long was it between the two calibrations? How much time did it take for you to
Talk for calibration like 3 months, but we used to work on this ion chamber 1.5 years.
I see. Well, the reference chambers, like the ones that we use, the specifications of those chambers say that the long-term stability to at least 1 year is about 1%. So if you have 1.25%, is a little bit higher than what the specification of those chambers are supposed to be. So I would advise you to, if I may, to perform a series of measurements the next 4 or 5 weeks, one measurement every week, to see if your numbers are the same. If your numbers are the same, then something more systematic has changed in your chamber, and you should use then the new calibration coefficient.
Okay, thank you, doctor, very much. Thank you very much. That is very helpful to me.
My pleasure.
So one of the questions, the messaging say, we talked about the TPR, the tissue phantom ratio. May you explain the TMR, please, the tissue maximum ratio?
The tissue maximum ratio is not a parameter that is important for us in the metrology. It's more important on the clinical side, and then it's more related to the maximum dose that each beam is provided in depth. TMR is not used as a parameter to define the quality of the beam.
Yes, thank you. Dr. Aladdin, you have a question? Raise your
hand. Thank you. Thank you, Dr. Almeida. Thank you for this useful information. Dr. Almeida, thank you very much. Dr. Almeida, generally speaking, each Linux machine and energy have its corresponding a set of beam data that comes from manufacturer. My question is, should this set of beam data be updated regularly or not? If so, what factor should be considered for determining the frequency of update? Thank you.
Okay, that's a very good question, because now everybody is generating those machines that they're calling a gold data. In other words, what they do is they tune the machines in the factory in a way that the percentage depth dose of that particular beam is pretty much the same for all the machines. This, in the later time, in the old times, this was not done. So every machine had a nominal energy, like say 6 MeV or 10 MeV. But if you did not define previously what was the point of Gmax, and then the percentage depth dose at 10 centimeters and at 20 centimeters, so you could somewhat define what the quality you want, they would come very different. Now it's more common that the machine comes, like I'd say, pre-commissioning at the factory. But does that doesn't necessarily mean that you should believe 100% in that data. You know, you should perform your measurements on some reference points to make sure that the Dmax is the same, that 5, 10, and 20, and 25 centimeters, you have the same numbers, at least for a range of field size. I think it's very interesting that manufacturers are doing that, and help a lot the people that don't have the means to like a sophisticated water phantom with a 3D movement to measure it. But I think you should do at least in 2D vision. You should make some measures to make sure that what you have is exactly what is supposed to be.
Thank you very much.
Thank you very much. We have Dr. Asad Hamid Ismail. Yes, Dr. Asad.
Good evening, everyone. Welcome, Prof, to the interesting presentation. Actually, I wanted to ask a general question about the radiation dose. In your opinion, my question is, in your opinion, do you agreement with the accepted level of radiation dose? Is it correct we say there should be an acceptable radiation dose, or as you say, safety dose?
That is a question more related to radiation protection, right?
I think so. Yes.
There's a more complicated answer for that, because you know, we don't have statistics that could enhance and could reduce the intervals between the radiation effect in the human and also the dose. If you, for instance, if we're talking about an uncertainty in our measurements in the radiotherapy in about 2-3%, in radiation protection about 10 to 15%, in diagnostic radiology is even more, because when you're talking about lower dose, in those below 100 millisieverts, the statistic is very poor, and you need 100,000, 200,000 people followed during the whole entire life to be able to define if that particular dose is to generate a new cancer. So to answer your question, the numbers that we use for radiation protections are more administrative numbers based on the level of knowledge that we have at the moment, or the level of ignorance that we have at the moment. So they come together. You know, we don't know very much. The radiation biology is not improving very much at this concept, because it depends on the statistics that we need to be able to provide a good answer. But I would say that the numbers that are generated by the RCRP that also provide the BIAA are normally the numbers that I use as administrative levels, and I think so far they are safe enough for us as a radiation workers.
I'm sorry, I mean the word of acceptable or safety regarding to the ALARA principle. In my opinion, there is not acceptable level, or there is not a safety level of radiation dose. That's I mean to give our opinion to you regarding to your experience about the radiation protection or radiation oncologists on.
Yeah, I think you are philosophically right in terms of say we cannot say that any what radiation is safe and what's not safe, but to be let's say just to be a little bit scientific, you know, one thing is that to know a particular effect below 100 millisieverts, which is the numbers that are mostly well known in the Japanese atomic bomb studies and the survivals, below 100 millisieverts, you know, what we have in extrapolation of the effect, it could be a linear extrapolation, could be over extrapolation. Even you have the hormesis, which is some people claim that low doses are beneficial to the individual. So below 100 millisieverts, you're absolutely right. We don't know. You can either say, I don't believe it's safe, or some people say we don't have enough information to say whether it's safe or not. So since we don't know, we better take a limits a bit higher for the work. Now, when you talk about secondary tumors, that may be generated in patients, that's also a very sophisticated question. And I'm very much afraid when we talk about extrapolation, because you as a physicist and as me, extrapolation could go to either direction. The interpretation could be in a different direction. But I'd say that when you say that there is no radiation limit with safe, we have to go again and remember that the radiation levels in our planet, changes with area, with altitude and so on. And all the epidemiological studies that have been done, even in Iran and also in China and in Brazil, that we have a very large area of very high radioactivity. There's no positive correlation between the doses and the effects. What has been observed in those areas is that when you're looking for those effects and the health system is implemented, you can identify cancers in an early stage, but you cannot say that they were generated by the environmental doses.
Thank you so much. Thank you.
Thank you very much. We have another question from Abdulrahman Abdul Baqi. Yes, please, Abdulrahman.
Hello, everyone. Thank you, Dr.
Hello.
Carlos, for this valuable presentation. My question is, what's the difference between absolute dosimetry and reference dosimetry?
Okay, let's go back to one of the first slides. Absolute dosimetry is when you measure the quantities in the absolute way. You measure charge per unit of mass, for instance, okay? Reference dosimetry is one you have to use a calibration coefficient that was provided by a lab that has used an absolute way, like a calorimeter, ferrosulfate, or a free air chamber, to provide you with a calibration coefficient of your chamber, because you don't know the absolute volume of your chamber. What you know is the nominal value. When you buy, it's a 0.6 cc chamber, this is a nominal value. When a primary standard, as I shown, it's 1 cc, is in fact 1 cc because it was measured 1 cc. So you cannot make an absolute measurement with a chamber that you don't know the volume. So that's the difference. You cannot measure the absorbed dose if you're not using a system that absorbs the energy per unit of mass.
Okay, thank you.
Great. Thank you very much. Yes. Do we have more questions?
There is an interesting question. They say, is there any other way to calibrate the ionization chamber to use it in a clinical side? Yes, you could use a ferrosulfate, for instance, but it's not very practical. You could use a calorimeter, but it's not very practical. But the ionization chamber seems to be the most practical instrument, which is well known. It's a system that has all interesting concepts because it's not equivalent to air, it's not equivalent to water, has a volume that creates a perturbation in the medium, but all those correction factors are well known, are well defined, and are well calculated even by Monte Carlo. So it becomes a very, very reliable instrument.
Thank you very much. Dr. Aladdin? Your mic, please, Dr. Aladdin. Your mic is closed.
Sorry about that. Thank you once again, Dr. Carlos. It was very useful information, informative lecture. We have just to say, if we can repeat this lecture or this event again for another topic, we will have you for that.
Isalaji, I don't know how happy I am to be able to speak to my colleagues in Iraq. You know, I had a colleague in this when I was in the States, you know, in school from Iraq, and I lost contact with him, and which was indeed was a very close to him as a friend. And please, you have my email, you have my directions. If you need any further information, if any of you need anything, just send me an email. And I don't promise to answer right away, but I will send an answer and I will send a guide for you. Okay.
Thank you very much.
Yeah, thank you very much, Dr. Carlos Almeida. We appreciate the information you provide us today, and we hope for another webinar and on the different topics. Thank you very much. Appreciate that.
Thank you. Thank you all.
Thank you. Bye.
Bye-bye.
Bye.
Bye-bye.